High-voltage power transformers are the beating heart of the electrical grid, routing massive amounts of energy to entire cities. When operators need to perform maintenance, they disconnect these towering machines from the grid. You would naturally assume that flipping the off switch leaves the transformer completely empty and inert, but that metal retains a memory. Due to magnetic hysteresis, the heavy iron core holds a permanent magnetic signature even after the electricity stops flowing. Engineers call this trapped magnetic fingerprint residual flux. Its exact strength and polarity are locked in place, completely dictated by the specific millisecond the power was cut. A de-energized transformer behaves like a loaded spring, holding a silent, invisible threat within its core. The danger arrives when a grid operator blindly flips the switch to turn the machine on, striking the transformer at a random point on the alternating current wave. If the incoming wave stacks perfectly on the trapped residual flux, it pushes the core's capacity past its limit. At saturation, it acts as a short circuit, drawing an inrush current, a surge 8 to 15 times normal capacity. Inside the machine, those extreme electromagnetic forces violently shake and warp the fragile, densely packed copper windings. Out on the network, protective relays misinterpret this massive power draw as a catastrophic short-circuit fault. They panic, instantly tripping the grid offline to protect the surrounding equipment. Random switching fails because the operator ignored the physics of the transformer's past, risking severe damage and total infrastructure failure. This presents an engineering dilemma. How can grid operators avoid a magnetic hazard they cannot physically see or measure once the power is off? The solution is the point-on-wave, or POW, controller, a diagnostic computer that monitors and logs the transformer's magnetic state during every switching operation. To figure out what's trapped inside the core, the controller has to step back in time. It actively watches the decaying voltage at the transformer's terminals at the exact moment the machine is shut down. This chart shows that mathematical calculation in action. By integrating the dying voltage wave, the controller calculates the exact magnitude of the trapped residual flux. It locks this value into memory, waiting patiently until the command to restart is given. By mapping the invisible threat beforehand, a dangerous game of chance becomes a predictable, solvable equation. When the re-energization command is finally given, the POW controller doesn't just throw a single switch. It initiates a highly coordinated sequence called independent pole operation, utilizing circuit breakers that can move each electrical phase completely independently. First, the controller checks its memory to identify which of the 3 electrical phases holds the highest trapped residual flux. Looking at this 3-phase chart, the controller fires that specific breaker at the exact millisecond the incoming source wave perfectly matches the trapped flux, resulting in zero magnetic collision. But there's a complication. Because the 3 phases share a single iron core, turning on phase A causes the magnetic flux in the 2 unclosed phases to dynamically shift and oscillate. The controller waits exactly 4.5 electrical cycles for the dynamic flux in those remaining 2 phases to align, and then fires both breakers simultaneously. Waking a multi-ton transformer requires a precisely timed mathematical ballet, one played out in fractions of a second. This oscilloscope capture shows the chaotic reality of a standard, uncontrolled grid switch. That massive, jagged spike on the left is the erratic voltage transient ripping through the system. By contrast, this capture shows the exact same equipment energized using a POW smart controller calculating residual flux. The spike is gone, replaced instantly by a smooth, stable sine wave. Eliminating this extreme mechanical stress extends the lifespan of multi-million-dollar transformers by decades and keeps protective relays from triggering cascading blackouts. By tracking the invisible memory of magnetic hysteresis, engineers bypass the violent physics of core saturation, securing the fragile heartbeat of our modern electrical grid.